Corrosion, a pervasive natural phenomenon, stands as a formidable adversary to engineering endeavors. It is the gradual deterioration of a material, typically a metal, resulting from chemical or electrochemical reactions with its environment. This insidious process can lead to significant structural damage, compromising the integrity, functionality, and longevity of engineered systems. From towering bridges to intricate pipelines, corrosion poses a constant threat, demanding vigilant attention from engineers across diverse disciplines. Understanding the mechanisms, types, and consequences of corrosion is paramount to mitigating its detrimental effects. The economic implications of corrosion are staggering, accounting for billions of dollars in maintenance, repair, and replacement costs annually. Moreover, corrosion-related failures can have severe consequences, including environmental damage, safety hazards, and even loss of life. Therefore, comprehending the intricacies of corrosion is not merely an academic exercise but a critical aspect of responsible engineering practice, ensuring the safety, reliability, and sustainability of our built environment. At its core, corrosion is an electrochemical process driven by the inherent tendency of metals to revert to their more stable, lower-energy oxide forms. This transformation is a natural process that occurs when metals are exposed to environmental conditions that promote oxidation. This natural inclination arises from the thermodynamic instability of most metals in their elemental state when exposed to oxidizing environments. Metals like iron, aluminum, and copper are particularly prone to this process as they seek to achieve a more stable state by reacting with elements such as oxygen. The corrosion process typically involves two primary reactions: an oxidation reaction, where metal atoms lose electrons, and a reduction reaction, where electrons are gained by species in the environment. These reactions are fundamental to the electrochemical nature of corrosion and are essential for understanding how and why metals degrade over time. These reactions occur simultaneously and are spatially separated, forming an electrochemical cell. This cell consists of an anode, where oxidation occurs, and a cathode, where reduction takes place. The separation of these sites is crucial for the continuation of the corrosion process. The metal surface undergoing oxidation acts as the anode, releasing electrons and forming metal ions. This release of electrons is a key step in the corrosion process, as it initiates the formation of rust and other corrosion products. These electrons flow through the metal to a cathodic site, where they participate in the reduction reaction. The movement of electrons from the anode to the cathode is facilitated by the conductive properties of the metal, allowing the corrosion process to continue. The electrolyte, typically a conductive liquid film on the metal surface, facilitates the movement of ions between the anode and cathode. This electrolyte can be water, salt water, or any other conductive liquid that comes into contact with the metal surface, playing a vital role in the overall corrosion process. The nature of the environment plays a crucial role in influencing the rate and extent of corrosion. Different environments can either accelerate or slow down the corrosion process, depending on various factors present in the surroundings. Factors such as temperature, humidity, pH, the presence of corrosive agents like chlorides or acids, and the availability of oxygen can significantly accelerate the corrosion process. High humidity levels, for example, provide more moisture, which acts as an electrolyte, thereby speeding up the corrosion. Similarly, acidic environments or the presence of salts can increase the rate of metal degradation. Understanding these factors is essential for developing effective corrosion prevention and control strategies. Corrosion manifests itself in various forms, each with its unique characteristics, mechanisms, and consequences. These forms of corrosion can significantly impact the longevity and safety of metal structures, making it crucial to understand their distinct features. Understanding these different types is essential for engineers to effectively diagnose corrosion problems and implement appropriate mitigation strategies. By recognizing the specific type of corrosion, engineers can tailor their approach to prevent further damage and extend the life of the structure. Galvanic corrosion occurs when two dissimilar metals are in electrical contact in the presence of an electrolyte. This type of corrosion is common in environments where metals are exposed to moisture, such as marine or industrial settings. The more active metal acts as the anode and corrodes preferentially, while the more noble metal acts as the cathode. This electrochemical process can lead to significant material loss in the anodic metal, necessitating careful material selection and protective measures. Pitting corrosion, as the name suggests, is characterized by the formation of small localized pits or cavities on the metal surface. These pits can be difficult to detect initially but can cause severe damage over time. This insidious form of corrosion can penetrate deep into the material, compromising its structural integrity while remaining largely undetected on the surface. Regular inspections and advanced detection techniques are essential to identify and address pitting corrosion before it leads to failure. Crevice corrosion occurs in confined spaces or crevices where stagnant solutions can accumulate. These areas are often found under gaskets, washers, or other components that create small gaps. These stagnant environments often become depleted in oxygen and enriched in corrosive species, leading to accelerated corrosion rates within the crevice. Preventing crevice corrosion involves ensuring proper design and maintenance to avoid the formation of such confined spaces. Stress corrosion cracking, or SCC, is a dangerous form of corrosion that occurs when a susceptible material is subjected to tensile stress in a corrosive environment. This type of corrosion is particularly concerning because it can lead to sudden and unexpected failures. The combined action of stress and corrosion can lead to crack initiation and propagation, ultimately resulting in catastrophic failure. Understanding the conditions that lead to SCC and implementing stress relief techniques and protective coatings can help mitigate this risk. By comprehensively understanding these various forms of corrosion, engineers can develop more effective strategies to protect metal structures, ensuring their safety and longevity. Regular monitoring, proper material selection, and preventive maintenance are key components in the fight against corrosion. Galvanic corrosion, a prevalent form of corrosion, arises from the electrochemical interaction between dissimilar metals in contact with an electrolyte. This type of corrosion is particularly common in environments where metals are exposed to moisture, such as marine settings or industrial applications involving water. This phenomenon hinges on the principle of the galvanic series, which ranks metals based on their relative nobility or tendency to corrode. The galvanic series is a crucial tool for engineers and scientists, as it helps predict which metals are more likely to corrode when paired together. When two dissimilar metals are electrically connected in the presence of an electrolyte, a galvanic cell forms. This cell generates an electric current due to the potential difference between the metals, leading to the corrosion of the more active metal. The more active metal, higher in the galvanic series, becomes the anode and corrodes preferentially. This process occurs because the anode metal loses electrons, which then flow to the cathode metal. Conversely, the more noble metal, lower in the galvanic series, acts as the cathode and is protected from corrosion. The cathode metal gains the electrons lost by the anode, thus remaining intact and uncorroded. The rate of galvanic corrosion depends on several factors, including the difference in nobility between the two metals, the relative areas of the anode and cathode, and the conductivity of the electrolyte. For instance, a larger surface area of the cathode compared to the anode can accelerate the corrosion process. A larger difference in nobility, a smaller anode area relative to the cathode, and a more conductive electrolyte all contribute to accelerated galvanic corrosion. Additionally, environmental factors such as temperature and pH levels of the electrolyte can also influence the rate of corrosion. Understanding the principles of galvanic corrosion is crucial for engineers to avoid material combinations that could lead to premature failure. By studying the galvanic series and the conditions that promote corrosion, engineers can design more durable and reliable structures. Selecting compatible materials, using insulation to prevent electrical contact, and employing cathodic protection are effective strategies to mitigate the risks of galvanic corrosion. Cathodic protection, for example, involves using a sacrificial anode to protect the main metal structure, ensuring its longevity and integrity. Regular maintenance and inspection of metal structures are also essential in managing galvanic corrosion. Applying protective coatings and conducting routine checks can help identify early signs of corrosion and prevent extensive damage. Education and collaboration among engineers and scientists play a vital role in advancing our understanding of galvanic corrosion. By sharing knowledge and working together, we can develop innovative solutions to combat this pervasive issue and enhance the durability of our infrastructure.